Well, I want to start out with something. All right, so I don't know if you guys saw this in Wired. This was in Wired a couple of days ago. Move over coders, physicists will soon rule Silicon Valley. And actually, I think it was very apropos because this is actually why I'm teaching this class. Because the point here is that physicists and the skills that we learn, that physicists develop as they go through their coursework and then as they start doing research, is really well suited for machine learning type of tasks. And this is what this says in many different ways. It says it's happening across Silicon Valley because structurally and technologically, because the things that just about every internet company needs to do are more and more suited to the skills set of a physicist. It is a particularly ripe moment for physicists and computer tech thanks to the rise of machine learning, where machines learn tasks by analyzing vast amounts of data. This new wave of data science and AI is something that suits physicists right down to their socks. These neural networks are just really just math on an enormous scale, mostly linear algebra and probability theory. This guy from Microsoft says, there's something very natural about a physicist going into machine learning, he says, more natural than a computer scientist. Physicists know how to handle data. So this guy from who works on LHC. I don't know this guy. He must be in the CMS data experiment. And building these enormous complex systems requires its own breed of abstract thought. They come because they are suited to the work, and they come because of the money. The salaries in tech are arguably absurd, but they also come because there are so many hard problems to solve. Machine learning will change not only how the world analyzes data, but how it builds software. In other words, all the physicists pushing into the realm of Silicon Valley engineering is a sign of much bigger change to come. Soon, all the Silicon Valley engineers will push into the realm of the physicists. So this is sort of the point that we'll see this throughout the class, and we'll see it in this first lecture a little bit. But what's going on right now is a sort of a transformation of Silicon Valley. If you go there, I mean, every other billboard that you'll see will say something like, we'll say name a company and say machine learning or AI or deep learning. Usually it doesn't mean anything, it's buzzwords for them, but everybody's sort of caught on this wave of new ways of doing, writing algorithms and doing intelligent things. And so and physicists are very well suited to doing these type of things. So this is, I think, something that's worth teaching you guys about. I want you guys. So my background is a physicist, and as a physicist, I was trained to do. I took a bunch of classes with a lot of math and a lot of those type of things for many, many years. And then you go and you finish all those classes, and you take you get in grad school, you take your qualifying exam, and then you start doing research. There, it's completely different. On your day-to-day, all of those calculations and things you do none of those things. What you do is you write code, because you have to mostly analyze data. And then you build all these skill sets that have to do with analyzing huge amounts of data and being able to make statements about nature based on those data sets. And it's that thinking that I think is very important. That's what I'm trying to give you guys a sense of, sort of introduce to you. I'm not going to be able to teach you everything that's necessary to do all this stuff. And the idea of this class really is to give you sort of an introduction, a starting point, a sense of how things work, and some practical examples that you can play around with. So it would be a starting point for you guys to then go do more research, go into things by just reading things on the internet and follow your interest to be able to develop these skills and maybe make yourself marketable for the outside world. That's sort of my goal. And there's a dual thing here. I think there's some of you who are physicists are here and interested about the particle physics part of things, right? Or some of you are not physicists but are still interested in that because it's kind of cool, the things that we do, and I'll show you some of that stuff. And then some of you guys are sort of more computer science and data science oriented, and sort of and this is the data sets and everything don't matter as much to you. But this ends up being a very good example, of how to do data science. So if you were taking most data science classes, you may start doing things with sort of small data sets and not realistic data sets. Here in this class, I will give you realistic data sets larger than probably most data scientists actually use in their day-to-day. So we will have access to those data sets and do things. Okay. So anyway, that's a little bit of introduction. Keep going. You guys probably must have read this, right? So pretty much says what I just said. I want to equip students with deep learning tools that they will use to learn HTTP concepts and techniques. This is intended for the guys who are either want to have an interest in a career in data science, machine learning, or deep learning, and are curious about particle physics. Okay? So this is the goal of this class. You guys know the time and place. Okay, so today's my plan is I'll give you guys a little bit of an intro. And the thing about this class is that it's a very difficult class to teach because I'm really touching on 3 complete fields, right? And I have to get you guys to know enough of those things to be able to do stuff. And my goal here isn't to, pedagogically go through everything, prove everything. That's not the point. In fact, I'll try to do as little math as possible. The math that we will end up doing is math that we're going to have to code up for particular type of things. It's really here about getting a sense of how things work and how things fit together. And in fact, this is a skill that I think is very important. Deep learning enables people to do, do sort of amazing things, to not write an amazing algorithm, but train amazing algorithms. And allows people to work in a domain they're not familiar with. They're the right algorithms in a domain they're not familiar with, but having detailed knowledge. So there are biotech companies now that use deep learning, but they don't have a single biologist on staff. Because deep learning is sort of, enables you to do that. So this skill of being able to work in a domain without being an expert in a domain is something that I want to get you guys to be comfortable with. And this is something that students are not usually very comfortable with. I mean, our typical grad student that comes in and I say, learn C++ or learn this thing, will go off and read a textbook cover to cover and try to understand everything. You can't do that in the real world. What you need to know, the important skill here is to be able to differentiate between things you have to know for what you're trying to accomplish and things that are not so relevant and sort of would be great to know and give you more understanding. So, and because it's impossible to know everything, right? So one of the things that I like to do in this class is to be able to give you that, just the things that you need to know, and the pointers to, if you need to know more about this particular topic because you're working on this thing, or you need more, here's where you go. Okay? That's the important skill. And we'll do that in the context of high-energy physics, but if you could get out of this class and get a job at Amazon or something like that, you will effectively do that. You won't know anything about their data sets and how the things work. You have to learn their systems and look up things and understand the data sets, all that stuff, right? So in some sense, you may go to Netflix or Amazon or Apple or Google or whatever, and they'll have data sets for you to play with. But that process of you learning about those data sets is similar to the process of you learning about the data sets here. Okay, so we want to exercise that. So what I have to cover is particle physics and high-energy physics. This is arguably one of the most difficult fields anybody can go to, because typically even our graduate students don't get to understand what we do until the 2nd or 3rd year, fundamentally understand, because you need to do, besides all your undergraduate stuff, you have to do quantum mechanics again, you have to learn quantum field theory, which I'll explain what that is, and then take a particle physics class, and it's very, very rigorous, very, very difficult. It takes a very long time. I'm not going to expect you guys to be able to do any of that. I do want you guys to appreciate what's there and how things fit together at an appropriate level, right? So that there's high-level concepts that you guys have to understand. And then the next is sort of data science, data engineering. This is just sort of the mechanics of handling large data sets. This is required for what we need to do in this class. For the most part, we try to actually sidestep that stuff. We have set up systems and we made things work, right? So I'll give you, most of the time, a working piece of code that does something, and then you have to go modify something, rather than having to start from scratch and figure something out. We'll do projects in the class, and they may be more doing things from scratch, okay? And then there's sort of computer science stuff. And I mean, on one side, there's a sort of branch of computer science. If you go down, the tree of computer science and all the different specialties, you can go down to artificial intelligence, which a subfield of artificial intelligence is machine learning, and a subfield of that is deep learning. So artificial intelligence is, it could be any type of system that, a computer can make decisions, based on inputs on its own. Okay. This could be a heuristic system, right? If you see the light turn red, then stop. That's artificial intelligence, believe it or not, right? Very simple. And in fact, until the mid-90s, that was how people thought that general intelligence would be solved. If you teach computer enough rules, then it'll go out and understand, how to deal with the world. Now, it ended up that it's very difficult to do that, and that doesn't work. And in fact, sometimes we have no idea how those algorithms work. And if you think about yourself, there's a lot of things that you can do that we have no idea how to code up. You can understand language, right? This is something that people have been trying to code up for a long time and had an extremely difficult time doing. You can process information around you. You can visual or audio information. These are things that have been very, very difficult to replicate in computers with algorithms, right? But if you can do something, we can take a machine and give it examples, and it can learn how to do that. You don't have to do that. So that's what. So machine learning sort of maybe in the past, maybe in 2000, started being a little bit more popular, and then now I'll tell you the story in a little bit. It's sort of deep learning, which is sort of the most powerful version of machine learning that is available for us to do, as has taken off. Okay. And there are additional sort of software engineering tasks here. Again, I'm trying to hide these things away from you guys, but you guys do need to know how to write code a little bit, and it will help to pick up some of those skills. Basically, it'll make things easier. Now, I don't expect you guys to have background in any of these. I expect you to have very little background. And I expect some people will be coming from the computer science background, so they know that stuff very well, so the software engineering part, maybe taking a machine learning class. Some people will come from the physics background, and so on. And I understand that. So the idea here is to have a class that is useful for all of you. So what I'm trying to do actually is to tailor the class individually. I want to understand what you know, what your skills are, and what your goals are. And we're going to try to help you get to those goals, okay? And it's going to be, unreasonable for me to expect, a computer science undergraduate student to be able to understand the physics concept at the same level as a physics graduate or undergraduate student, and vice versa. And so in my grading, I will try to take that into account, okay, and how we do things. So the aim here is to understand enough to be able to apply deep learning to HEP, and not necessarily much more than that. We're going to be very, very pragmatic, okay? And then once you do this, as I was saying, the idea is that you'll be able to apply deep learning to any domain. So you sort of have done it in one domain, you can apply it in any domain. There'll be no formal proofs. There'll be minimal math and minimal coding as much as I possibly can, okay? In terms of, as I said, the logistics, I'm going to try to tailor class and grading to each individual. The one thing that's going to have to happen today is that I want everybody to sign up for an account. So I have a cluster that I've set up. It's in my office right now. We're going to do all the homework there. It's got GPUs, which are necessary for training the networks. It's got lots of the data sitting on big array of disks, those type of things. So everything's going to happen there. So one of the things we're going to have to do today is everybody needs to, who doesn't have an account, and quite a few of you do actually, needs to get an account. I'll give you instructions on how to do that a little bit. Okay. That's what Grayson's here actually. All right, so why deep learning, why physics, and why high-energy physics in particular, okay? So just to think a little bit about ourselves, our brains, or any brain of any animal, takes in sensory data, right? And actually what we end up doing is we build some sort of hierarchical models. Our brains build hierarchical models of the outside world. For example, if you look at the visual cortex, and they do experiments like this, they take cats and cut up their brains and they look into at the individual sort of neurons and try to detect which neurons are being activated. They can present things to cats, and they'll see that if they give like horizontal lines, there are particular neurons that get activated, and vertical lines, other ones, and so on. So you can see that what happens is that there somehow, whatever visual information you get, there are some sort of neurons that get triggered if that thing is in your view. Okay. So they're sort of detectors. And these are what we call as sort of features. So a line or a change in contrast or something like that is a feature in the your visual field. And you have feature detectors, a neuron that somehow sits there, and whenever that sits there, it lights up. Okay? And then what happens is that you may have, there's a hierarchy of features. So there's lower level features would be sort of contrast and lines and things like that. But if you have a bunch of lines put together in a particular way, then that constitutes a circle. And so there are high level features, which, neurons, that when they notice, oh, I have a bunch of these low level features in this pattern activated, and that means I see a circle, right? And then above that, there may be, well, I see a circle and I see two other circles inside. Well, that's a human face. So that's what I mean by sort of hierarchical feature detection. Okay? And the way it works is that actually by doing that, when I'm looking at this room and looking at you guys, I have this sense that I can see everything in this room. But in fact, my eyes have a very small field of view. And what's going on is that my eyes are constantly scanning, and I'm building this model of this room in my head. And that keeps track of, there's a wall over there, and these people are sitting here, and those type of things. Even though I'm not seeing over there, I have this feeling that this person is here, because I built this sort of model of the world. Okay? In fact, we don't really, what we believe is being reality is actually whatever our brain sort of projects. This is why people have hallucinations and see things that seem real to them. We don't really, I'm not really seeing you. What it is that there is a pattern that's being, established in my brain that corresponds to something that I recognize as you, in my brain. I don't know. That's what seeing really is. Okay. So there's interesting sort of experiments that people do. There are actually, for example, neurons that keep track of where you are. They're like mapping neurons. So when I'm in this room, there's a neuron that's keeping track of the fact that I'm here. And as I walk forward, other neurons in my head turn on that let me know I'm now changed where I am. Okay? And you can do experiments actually on rats and cats and things like that. I can see these things happening. And what's interesting is that if I went over there and this neuron got activated, but if I imagine going there or think about going over there, you see that the same neurons get activated. So what I've done is I built a model of the world in my brain, right? And different things represent different things, right? And those things will get activated if I have a sensory input. But if I start thinking about those things, I'll get the similar sort of activations. So that representation of the real world gets activated as I'm imagining and thinking about things. Okay? So that's how our brains work. Okay? And so what happens is that when I want to make a decision, like I want to go from here to there, I have this model of this room, and in that model there's this table, so I understand I have to walk around this table. Okay? So I make a prediction. If I want to go there, if I walk straight, I'm going to hit the table, therefore I'm going to go around. This is how our brains work. Okay? I mean, this is somewhat obvious, and it's so that you don't notice it, but that's how it works underneath. Now, neural networks, artificial neural networks, which I will talk about more, maybe not today, in detail, are an attempt to be able to reproduce that. And deep networks are effectively, originally the neural networks were made where they would have some input that comes in, they will have some layer of hidden neurons, and they would have one single, and then we'll have the output. So we have a single layer in between. Now, the reason for that was, and I can explain if we get to today, was a technical problem that they couldn't have neural networks that have multiple layers on top of each other. They couldn't train them. Until recently, they didn't know how to do that very well, or very effectively. Okay? But the thing that's happened in the past 10 years is that we've learned to be able to do these type of things, to train networks that are really, really deep. And the result is, when you do train these things on pictures and those type of things, you see the same hierarchical sort of thing that you see in the visual cortex actually appear. So if you take these neurons and start identifying these neurons as feature detectors, you see that these neurons, some of them at a low level, will start identifying sort of contrast. And no matter what kind of picture you give, they work the same, right? And then you go a little bit deeper, and you see those neurons are activating different type of things. So if you look at pictures, there'll be a set of neurons that activate ears and eyes and those type of things. And if you're looking at cars, there'll be parts of cars and animals and so on. And then when you go higher, there are other neurons that activate on full, faces and so on. So that same pattern that I just described is what we see here. In fact, I have a friend, a childhood friend that is a professor at Stanford, who, what he does is that his research is, he wants to understand the human brain. But the way he does it is by building deep neural networks and training them to do things, and then understanding how those representations, got built and what those representations mean. Okay? So you can do, he's a neuroscience professor, and he does neuroscience by working on deep neural networks. Okay? As a way of doing it. All right. Then let's come to physics. So why physics? Well, to understand the most fundamental, laws and aspects of nature and phenomena in nature, what physicists have been doing for hundreds of years are actually that we define as the scientific method. And the scientific method, sort of implicitly in it, is, there's this idea of having a hypothesis. The hypothesis, for a physicist, really is a model, right? So, for example, Newtonian mechanics is a model of how we believe things should work in the world. It's got a set of rules. It's this particular type of model. And so that's what physicists do. They build models. And then when the models don't do very well or fail in some domain, they'll build better models and more sophisticated models. And that's the sort of the way things work. So here we're going to talk about high-energy physics. The big model of high-energy physics is called the Standard Model. Got the word model in it, okay? And it describes the building blocks of matter, like all the things that we know, all the particles we know that exist, the most fundamental particles, which then come together to make all the things that we are made of, and the interactions with those particles. Okay. Now, because that's the theory, we write this thing. We say there are these particles. When you write the model, when we were writing them originally, there were parts of the model that we hadn't observed yet. To make the model consistent and work, there were particles that it predicted that should exist because that would make the model consistent, but hadn't been seen yet. And so there was a whole campaign for the past 30, 40 years to actually go back and try to find those particles. And what's happened in the past, since 2012, we found that the last remaining particle as a part of the Standard Model. Okay, in fact, a very critical one. Okay, and right. So what the Standard Model does is says, okay, there's these particles, and if you haven't seen them, if you have seen them, it should have these properties, and if you haven't seen them, this should be this particle with these properties. And then you do experiments of measuring the properties of particles you've seen, and looking for the particles you haven't seen, and so on until you see them, and you check if it's consistent with the model. Okay. And the kind of frustrating thing that has happened with the Standard Model is that it's actually been super good. Everything that we predicted came. Everything all the calculations that we do agree with experimental results. And some of them, actually, the most precise measurements mankind ever made has been of, aspects that have to do with this model. Okay, to n decimal places, measuring something and matching it to computations of the same thing. Okay, in these models. Nonetheless, these models have failures. For example, it's not a complete model. It doesn't have dark matter, and dark matter is something we know is a big part of the universe. There's no dark matter candidate there. That fails in that way. It also has some. It's not the Standard Model doesn't include gravity. There's a mathematical problem. We don't know how to do it actually. It also has inconsistencies. Oddly enough, the Standard Model, the Higgs particle is a key component of the Standard Model. It predicts the Higgs particle. And it needs the Higgs particle to have a low mass for the Standard Model to work. But then when you go to calculate the mass of the Standard Model, of the Higgs within the Standard Model, it ends up giving you an infinity, basically telling you it's going to be very, very large. So there's this weird inconsistency that says the Higgs has to be light for everything to work. And now we've seen the Higgs and we know it's light, but then when you do the computation of what the Higgs mass should be, it's very, very large. That's the inconsistency. That's called the hierarchy problem, and that's actually the main driver now at LHC. Okay. All right, so that's the Standard Model that we built. Now, the other thing that's relevant here is that now these models are expressed mathematically, right? What physicists like to do, they're reductionists. We like to have the least amount of assumptions, right? So they'll write down a certain minimal set of laws or principles, some rules of the model, right? And then use math. They'll use some mathematical framework to describe this stuff. The mathematical framework that we use is something called quantum field theory, which is way beyond this class, but I will explain a little bit more about it and where it comes from in this lecture or next, just so you have a sense of it. They use that framework and apply it, which encapsulates some of these rules and put additional rules on that. And based on that's how you write down the model, so mathematical model. The Standard Model really is a model in that we don't believe the Standard Model is actually reality, what's going on at low level. Because of these inconsistencies and failures, we know there are places that it doesn't work out. In fact, the Standard Model, there are things that you go calculate and it kind of doesn't quite work out because when you take the Standard Model and extrapolate to high energies, for example, we have never done experiments at high energy. We don't know how things go, and the prediction of the Standard Model at high energy is not reasonable. So what we do is we take all those high energy sort of things. There's a technique called renormalization where you can take the things that you don't know and you can encapsulate it in some parameter that you can measure. So I don't know this thing, but I can go and measure the mass of this particle, and once I measure the mass of this particle, that's encapsulated in this mass, and then I can use the mass everywhere, and this thing I don't understand is correctly accounted for. It's analogous to like a spring constant for Hooke's law. You remember Hooke's law from your first physics class, right? The force that a spring exerts, right, is proportional to the how much you extend it. So if I have a spring and I pull it, if it has length L and I pull it to length 2L, the force that you feel will be twice as much, right? That's what it says. But actually, that's a very simple model of a spring. A spring is really a coil, right, of typically metal, stuck together in some way, and that elastic property of the spring is a very complicated thing. But it ends up, for our purposes, it's very well approximated by this. If I went to actually want to model the spring at that small level of every single atom interacting, it would be very, very difficult to do that. And for a wide range of lengths of springs for stationary springs, this model works really well. But if you take the spring and you pull it a lot, and you actually start uncoiling it, this doesn't work anymore, right? There are regimes that it doesn't work. And that's analogous to the standard model. Standard model has parameters like this, right? Which things that we don't understand, we can encapsulate in some parameter. Now, how do you know the spring constant of a spring? You go and you hang your weight from it and you measure, right? And we do the equivalent of that. We do measurements, okay? And a standard model has 19 parameters, okay, that we measure. But once you know those 19 parameters, it predicts everything precisely and perfectly, okay? But it tells you that it is not a fundamental thing, because there are things that we don't know, and we're encapsulating these parameters, okay? And one of the things we want to do is actually have a fundamental understanding. All right, so that's what standard model is. So what do we do? We build a model. Now we want to improve the model. We know there's problems with it. So what we do is we then postulate new models. We'll take the standard model and postulate a new model. We'll add to it. Now we have to, whatever model we have to have has to be consistent with the standard model in the places that a standard model works, right? So it's going to be, something. It can't be something completely radical and change everything, because that'll break the standard model. And typically we'll do that if we can, not empirically, by just adding something. We'll say, aha, there's maybe this new symmetry of space-time. And that new symmetry of space-time, therefore, will give you new particles. And those new particles will solve this problem that we're having. So the Harker problem is actually solved by postulating. One of the ways of solving it is postulating that there's something called supersymmetry, which says for every particle there's a partner particle, and then those calculations that we do that makes the mass of Higgs go up, the partner particles give you counter terms that cancel the particles that were in the standard model, and the Higgs mass doesn't blow up. That's how it works. Okay, but you just if we can, we'll come up with some new rule, and it's great when you can apply one new rule, and based on that, you get a bunch of things. Actually, that's why people like supersymmetry, because not only does that, it also gives you a dark matter candidate, and it makes all the forces at high energy come into one force. It says all these nice sort of features. But it's just postulating really one new idea, okay, which is kind of neat. And then, so what we do is we'll build models like this to address our problems, right? Preserving consistency with existing experimental evidence. And then we'll make predictions. And usually the predictions are, okay, status physics, supersymmetry, says there's going to be new particles, right? And then, so those are the predictions. And then based on those predictions, what we'll do is we'll go and create experiments. So we'll make experiments saying there was this particle that is, postulated by supersymmetry. We want to look for it. How would I need to do that? I need to build an accelerator and so on. So the Large Hadron Collider is this, right? Now, the Large Hadron Collider, as I said, found the last and most critically important part of the standard model. There's actually this Higgs. The Higgs mechanism in the standard model is a critical thing in how it works, and maybe I'll get to it a little bit today. And now looking for, okay, so but we found this particle and everything's okay in some sense, and everything came out to be consistent. We're still trying to make sure that this is the standard model version of the Higgs. And now what we're doing is actually now trying to solve that hierarchy problem. We're looking for particles like supersymmetric particles, okay? And for those particles to work, they have to have masses in what's called a TeV. TeV is a unit of energy, which Einstein told us energy and mass are the same. So 1 GeV, that's giga electron volts, is about the mass of a proton. So this is about 1,000 times the mass of a proton. Okay? And so those particles should be there, have masses around those, if they're going to solve these problems. Okay? So let's talk about a standard model. Okay. So I want to build a model of the universe, right? Or what I want to do is actually be able to, let's say, I want to actually create a universe. I want to say, okay, I have a model. How can I get this model to actually, if I did the computations, or if I can actually somehow instantiate this model in reality, what it needs to do to be able to, make the universe. Well, the thing about a universe is, the first thing you guys, what do you mean by the universe? Well, the universe is defined by different sets of structures in the universe. At the very, very largest scales, we see the galaxies, right? And within those, we see, stars and planets and things like our solar system, and we go down to the stars and the Earth and so on. Those are structures that are made. These structures are all sort of pulled together because of gravity. But then if you go smaller and smaller to sort of here, you're going from, these are thousands of kilometers, right, to the millimeter scale, you start seeing additional types of structures. So matter that we are familiar with and we deal with, at the level that our intuition, really we are comfortable to up to the sub-millimeter sort of level, okay? But when we start getting down to molecules, which are, stick together to make sort of matter, or atoms which make these things, funny things happen. You have to start doing quantum mechanics, and these kind of funny sort of, your models have to get much more sophisticated to do that. And then you go all the way down from the molecule down to an atom, and you take the atom and you focus on the nucleus, and you look at the nucleus, you see that they have protons and neutrons, and then you look at the neutrons, and you see that those are made out of quarks. Okay? And these are all different structures. So the universe, actually, what it is that it's a bunch of quarks that stuck together to make baryons, like protons and neutrons, which stuck together to make nuclei, which stuck to electrons to make atoms, which stuck together to make molecules that constitute matter, which then come out in large scale to make Earth and everything else. Okay? So it's a sort of a hierarchical, nature is hierarchical. In fact, this is actually, there is papers on deep learning that say that the reason deep learning works is because nature is hierarchical, actually. They can actually prove that. So this is just the same slide, just pointing out that to build those structures, right, I need to be able to get things to stick together. So to get the nucleus to stick together and the baryons stick together, there's a particular force. You can see there's a certain scale for these things. This is a very strong force that binds these things together. It's called the strong force. Okay? That's what pulls those together. To keep the electrons and going around the atom, that's the electromagnetic force. In fact, the electromagnetic and this other force called the weak force combined is together called the electroweak force, which is maybe 50 times weaker than the strong force. Okay, and that basically governs that electromagnetic force. Is actually governs all the physics of atoms, of molecules, and matter as far as we know. And then at the larger scales, there's gravity that pulls everything together. And gravity is the weakest thing. And the thing to notice is that the stronger the force, the tighter the things stuck to each other, the smaller the structure. The weaker the force, the opposite. And gravity is very, very weak, actually. A few words about our mathematical model. So I expect that all of you guys took, 1440 something, right? And so you have some familiarity with these things, right? So you guys are, and what you learn is that basically you build this model of particles being something that's, any object is something in space, and it's got a position, and it's got a velocity at a given point, and then use calculus to be able to predict, given the position of velocity now, where it's going to be in the future, right? That's basically what you guys learn, right? Now, it ends up that if you wanted to apply the same thing and go to very, very small scales, things don't work out that way. Nature ends up being very kind of strange, and what happens is that you no longer can make a prediction that if I have a particle here and I shoot it that way, it will end up here. You can only get the prediction that it will end up there with a certain probability. And so the mechanics and the computations you do cannot be precise at some level. It's not precision, but it's precise, it's deterministic, but it's a probabilistic. So that if I have exactly the same setup and I throw this particle going this way, it may end up here, it may end up there, it may end up here, but if I do it many, many times, you'll have a certain profile of probability of where it ends up. And that's what quantum mechanics sort of predicts for you. Okay? It also ends up that if you go, I guess I'm not doing relativism here. Okay. So the other thing was that you guys, I'm sure most of you took E&M, right? So you took 1442 or 4, right? And there, you learned about something very different. It wasn't like single particles. You learned about these fields that permeate space, right? And these fields have a value everywhere in space. And it's those interactions of those fields that make things happen. And in fact, the photon is a wave on those fields. That's what you guys learned in that class, right? That is a very different view of things. Here, the particle is some point-like thing. Here, the particle, like the photon, is a wave on a field that's functioned as a value everywhere in space, right? That you can't see, but if you get a wave in there, that's actually what a photon is, right? So ends up that's actually the description. This is called field theory, and this description is the model of particles. So quantum field theory, which I'm going to get to in a second, fundamentally is a field theory. It's a theory that all particles are some field that permeates space that has some value at any given point in space. And depending on the spin of that field, it only has 1, 2, or 3 values, okay, at any point in space. That's what a field is. And then if you go this way, so now the other funny thing is that if you take, when we started from Newtonian mechanics, we went to very, very small. We saw we had to need quantum mechanics and funny things happen. And so if you start going very, very fast, funny things also happen. There you need relativistic mechanics. And so quantum field theory, it's sort of all these things put together. You have a field theory, which is relativistic, and it has quantum mechanics all put together. And that's what quantum field theory is. Okay? That's as much as you guys need to know. I just wanted you guys to get a sense of what these words mean. The field means that there's a particle over space. The quantum part means that everything is probabilistic that you can calculate. And fundamentally is relativistic. Okay. All right, so then if I wanted to build a static model, so this is the way I would say it. If there was an alien race that came down and said, we want to know what you guys know about physics. And let's say they're super good at math. So they understand all the equations that right now. We'll say, well, we know this thing called field theory. Here are the rules. They're like, oh, I got it. That took me 5 minutes. And then you say, okay, so what we know is that these particles exist. Okay? So the fundamental particles that we know exist are divided into quarks and leptons. Lepton for light, quarks for spark. And then the quarks, they come in generations. So there is 1, 2, 3 generations. And you see that each of the generations, the quarks and leptons have pairs. There's an up and down quark, it changes a charm and strange quark, and top and bottom quark. And then associated with them, there is the electron neutrino, muon neutrino, tau neutrino. Everything that we know that exists is made out of this stuff. You, me, and everything. In fact, everything you know that naturally comes around us with this stuff. Some of this stuff naturally happens. It's very hard in nature to make these things. But we can make all these things in the lab. Okay, that's the first ingredient. You say, so these are these particles, and these are sort of, you say some of this quantum numbers, what are the properties of particles. And then the next thing you do is something very beautiful. Instead of saying there's forces, what you say is that there are these symmetries of nature. There's something called a gauge symmetry. And basically it says the symmetry is something like this, that if you take one of these fields and you do a funny operation in space and move it around, there should be some invariance. So if you do something to this field, to do some operations, it shouldn't change. That's what a symmetry means. That means that I mathematically do something to the equation, and then when you carry all the math through, the equation comes back and looks exactly the same. Okay? So that it's invariant under that whatever change I did. Okay? So you postulate 3 what's called gauge symmetries. There's a particular way of doing these symmetries. And each of those symmetries, if you follow it through, for those symmetries to be true, an additional field or additional set of fields have to exist. And those additional set of fields that have to exist for that symmetry to be true end up being the photon, and a W, and a Z, and the gluon. These are the mediators of the forces. And the effect that they have is the forces. So it says that, okay, if I want, here, when I started out, I said there are these particles, but these fields exist everywhere, but they don't interact with each other. All I say is these fields obey these symmetries, and then these other fields have to exist that connect between these fields so that allow interactions. So an electron interacting with another electron interacting with a muon, what happens is that electron and muon don't directly interact. They'll interact with this new field, like the photon field, and then, so the electron interacts with the photon propagates, and then it interacts back with the muon, and then you have an interaction with the electron and muon. And that's why there's a force between an electron and muon, for example. Okay? So that's the third thing. The second thing. And the third thing is that, so far, I actually didn't give you the mass of the particles. This is a massless theory. And actually, in a massless theory, everything would move at the speed of light, and no bound states were made, nothing would exist. Obviously, that's not true. So you need to actually give mass to things. The problem is that if you put mass by hand in the theory breaks. These gauge symmetries break. So the way that we do mass is that we say there's another field that exists all through space, and every particle sticks to this field. And the funny thing about this field is all other fields, when there's nothing around, the value is 0. But this field in the empty space of the universe has a non-zero value. And since it interacts with everything, the effect of that field being there is the same as mass. It's effectively like if you go and you're in a swimming pool, right, and you walk around, it's a little bit harder for you. You have a drag on the water. That water's interacting with you. And that effect could be represented as an additional mass that you pick up. So it's sort of a similar type of thing. This Higgs field's there, it sticks to everything, it's got some non-zero value, and so everything sticks to it and picks up some mass. And so we pick up mass dynamically. Mass is not something that's inherent to particles, it picks up dynamically through interactions to the Higgs. And this is why the Higgs is very, very important. In fact, most of the parameters of the standard model, the 19 parameters of the standard model, have to do with or just how much does each particle interact with the Higgs field. Okay? So you put all those things together, and you get the standard model. That's all you need. And that's what I mean by a limited set of rules. Okay? We start with a very similar, small, limited set of rules, and we get this stuff. Okay? And everything you do, it agrees with experiments. Okay? And so then, just to say that the picture of the interaction then is that if I have two particles interacting, particle 1 and particle 2, they may come together and interact. So this is one coming here, one coming that way. So maybe 2 electrons or something like that. And they may exchange. Actually, this is a bad picture. I should have done it. My arrows are bad. Should have noticed that earlier. Let me go back to this one. Arrows are bad. What I wanted to say, if you have like an electron coming this way, another one coming this way, they'll interact by exchanging a photon and go out. But I didn't draw the arrows right. But that's the idea. We'll do this stuff more again. I don't want to get stuck in. Let me just tell you a little bit about testing a standard model. Boy, I'm already out of time. So let me skip a little bit and. So I'll continue with this stuff next time. I want to say a couple of words about deep learning. I'll probably keep you guys a couple of minutes more. Okay, so deep learning. We'll go through this, and you guys probably have seen my talk. But basically, as I said, these are things that try to mimic what happens in the brain. We couldn't build really deep networks, multi-layer networks. And what happened was that we came up with some techniques that allow us to do that. I'll explain those techniques to you as we get them. We also got much more data. So if you have more data, it's easier to train these things. And then because you have a lot of data, to train these things, you need a lot of computing power. GPUs came along and provided us a boost in computing power. So we can, so there's a sort of a trifecta of new techniques, big data, and GPUs that suddenly enabled us to be able to train really big networks. And that's why deep neural networks are sort of a big thing. Okay? I'm sure you guys have seen some of this stuff in some of my talks. I won't say it, but these things can do amazing things. They can. This is showing, for example, image recognition. They are now at a point where this is, if you extend this to where it is today, using deep neural networks, computers can identify images better than human beings now. They have superhuman performance, for example. These are just some examples of those things. Here's an example of, you can keep one of these, if you build the right type of network, you can give it an image, and then it will generate a caption for you. For example, you can do some crazy things these days. Just making a point that there's a whole lots of different types of deep neural networks, okay? And we'll talk about a few of these during this course. There's just not one type. There are different types, and they're suited for different types of problems. Let me just also say, why do we want to go deep, right? One is that we can get better algorithms, right? That means that algorithms that I don't know how to write the algorithm to drive a car, but I can teach a machine to learn how to drive a car. In fact, that's how driverless cars have come around. People did it through machine learning, not by writing heuristics. Okay? I may know how to write an algorithm, but it might take a lot of time and effort to do that. So maybe I should be able to instead do an easier algorithm development, right? That's the other thing. And the other thing is that it could actually be faster. Our brains use 20 watts of power, okay, compared to 100 watts on most CPUs that you can have and so on, and are much, much more effective. They're highly parallel systems, right? And it's because it ends up, these sort of techniques are very, very efficient in computation. So even though I'm able to write an algorithm, a deep neural network that reproduces the results of that algorithm may be faster than the original algorithm. Okay? So it may be able to replace it. And it may be that algorithm, when I code it up, is really hard to write for a GPU. But now in a deep neural network, it's just math that GPUs are really good at. So the code gets replaced by weights and on connections, which represent connections between neurons. The code that I would have written out, all this stuff, is just weights in the matrix, and these GPUs can churn those very, very easily. Okay, so I got to talk about this class. So some logistics. So lectures are going to be recorded with the ecosystem. Okay, so you guys can always go back. I'm going to try to settle into a pattern where we'll get to, so Monday we'll do like a physics lecture. Wednesday I'll do sort of a machine learning, deep learning lecture. And then Friday what I want to do is actually do sort of a lab. What I want is I'm going to plug in my computer and do work in front of you guys. And in fact, what I'm mostly going to do is introduce the data sets and show you how to manipulate it during that time. Okay, that's sort of the pattern we're going to eventually get to. Okay, I would like you to bring your laptop every time, but for sure bring it to the lab sessions. And you know when the lab sessions are; it's on the syllabus. Okay, so bring the laptops with you guys. If you don't have a laptop, you can get one from the library. I'm sure you guys all have laptops. Okay. One thing you should do today. This is your homework. Write an email to Grayson. Grayson's sitting there. This is his email address. With your preferred username. So he needs to know what username you want. So whatever username is your favorite username,